All right, here we are. Let me mute the TV and let's take a look at example 6. Um, kind of trying to make up for our little snow days that we've had and have a good record of these examples, putting everything together that you've learned in calculus so far. In example 6, taking a look at it, again, thinking about our domain, it's a cube root, so there's no restrictions. So our domain is going to be negative infinity to infinity. However, because we have the odd roots there, I'm going to be like there's a cusp or vertical tangent line alert that I do need to be careful about whether or not there might be a cusp or a vertical tangent line. The other thing is, in looking at this, I would probably go ahead and do a quick factoring. If you pull out, remember you want to pull out the smaller of the two powers, so I'm going to pull out x to the 4/3. And you subtract your exponents. 5/3 minus 4/3 would be 2x to the 1/3 minus 5. And so in doing that fairly quickly, because it factors fairly nicely, I do know that we're also going to have x-intercepts at x equal to 0 and at x equal to the 5/2 cubed. Right, I'm just solving in my head, and you can check my algebra on that, but add 5, divide by 2. So that would be 2.5, and then we are going to cube it, whatever that is. And the good thing about AP is you don't have to actually simplify that. When we go to sketch it, we'll let Desmos go ahead and add that in. So I want to go ahead now. I know that our function f is continuous because it's the sum of continuous functions with that domain. Although I am going to kind of say, not quite sure about the differentiability. I'm going to make a note to myself that there's a cusp or vertical tangent alert because of those cube roots. Might have a vertical tangent line or something going on that I need to be concerned with. So we'll see that when we take the derivative and we see whether or not the derivative has any discontinuities on it, then we'll know whether we have that cusp or vertical tangent alert because of the domain being negative infinity to infinity. So let's go ahead and let's find our first derivative. So easy power rules. So we would have 2 times 5/3, 10/3 x to the subtract 1 2/3 minus, again multiply, 20/3 x and subtract 1 to the 1/3. And now taking a look at that, it does have a domain of negative infinity to infinity and does not have any discontinuities. So right there, just by looking at this derivative, I now know that it was continuous and differentiable when I was taking a look at it in terms of the first derivative. And so now we've taken care of that. I'm going to go ahead and factor this to get my critical values. Let's take out 10/3 x to the 1/3, again, smallest power, is going to leave me with x to the 1/3 minus 2. And so solving that, we're going to have critical values at 0 from the x to the 1/3 equaling 0, and at x to the 1/3 equal to 2, or x equal to 2 cubed, which is going to be 8. So 0 and 8 are going to be our critical values. We can take a look at our sign chart, and we can put on our 0 and our 8, both of which are 0. So f prime, check our signs. This is going to be negative in this section. This one, you've put -10, or even if I put like -8, well, actually we got to, yeah, -8 is going to be -2. It's going to be a negative and a negative, so that would be positive. If I pick something in between here, easiest would probably be 1. That would be positive. 1 minus 2 would be negative, so we would have a negative. And then picking something larger would give me a positive and a positive. So we know that f is increasing and then decreasing and then increasing. So there is going to be a local max at x equal to 0 because our f prime switched plus to minus. There's going to be a local min at x equal to 8 because f prime switched minus 2 plus. And we're going to need them, and we'll let the computer figure it out, but 0, f of 0 is actually going to be 0, 0. That one's really easy. And then if I put in the 8, that's also pretty easy because I'm going to do the cube root of 8 is 2, 2 to the 5th is 32, 2 times 32, that would be 64 minus cube root of 8 is 2, 2 to the 4th is 16, and then 5 times 16 is 80, so minus 80. So we should end up with negative 16, I believe. But again, we'll check that on the computer as we take a look at it. All right, and then we're going to go to our second derivative and find out concavity. And so f double prime is going to be equal to, again, nice product rule. So I'm going to come back up here, multiply. So that would be 20/9 x to the negative 1/3 minus 20/9 x to the negative 2/3. Go ahead and factor out the 20/9, and then x to the negative 2/3 would be the smallest power. Then subtracting negative 1/3 minus negative 2/3 would be x to the positive 1/3 minus 1. And so taking a look at that, then we want to figure out what our point of inflection is. And there is going to be a possible POI. Okay. Technically this is a fraction, x to the 1/3 minus 1 over times 20 over 9, and then cube root of x squared. Possible POIs, you do want to look at where the second derivative is equal to 0, which is going to be at x equal to 1. And we want to look at where the second derivative does not exist, which is going to happen at x equal to 0. Now, this may not be an actual point of inflection, but remember, it is still a possible point of inflection taking a look at it. So then we go down to and we do our sign chart. So we check and see what happens. So we have our 0 and our 1. This is our second derivative, which is undefined here. And then it is 0 there. We check our signs. This, because it's squared, is always positive, so I'm really only looking at this. And this is going to be negative below 1 and positive above 1. So negative, negative, positive. So we're going to have f is going to be concave down, and then concave up. So notice this 0, while it technically is a possible point of inflection from the second derivative, is not actually a point of inflection. The only point of inflection is at x equal to 0 because your second derivative switched minus 2 plus. We could have just said switched signs, because I'm going to go ahead and do that. Because remember, we don't really care what it switched. We only care that it switched signs for the second derivative. Right? Let's take a look at our actual graph and see kind of what's going on here. So notice here's my 0, f of 0, and we'll show the label. That's your relative max. Then I have our 8, f of 8, and that's my relative min. That's down here. And then my 1, f of 1, I add that in. That's right here. It's going to be my point of inflection. Now remember, there was also that point that was the x-intercept, which, let's see if I remember where we had that, at 2.5 cubed. So I can add that in, excuse me, I have to type that in. So 2.5, and then we will cube that, and then put a comma. And then you see, that's the nice thing about this notation. We can actually just tell it to do it. Do f of 2.5, and then cube it again, cubed, and then we can close that out. And that will give us our label for our x-intercept that we had on there. Now, one last thing before I do my sketch, I do want to figure out my end behavior to see where it goes. So let's come back over here. I'm going to come up here and I want to do the limit. Yeah, I'm on that. So we'll just put it on top of the graph because y'all, the graph is going to be there for you guys. So the limit as x goes to infinity of f of x. And so if we take a look at this cube root to the fifth and fourth, remember you just go to the higher power, which is this one. It kind of acts like polynomials. And this is going to be going to infinity, albeit maybe not as fast as, without having the cube root there, but it's going to be going to infinity. Dominating term wins. And the limit as x goes to negative infinity of f of x. Again, we go by that dominating function. And if you take a look at that, because it's all odd powers, cube root's going to be negative, a negative to a fifth power is going to be negative. We're going to be going to negative infinity. So we don't have any concerns because maybe there might have been a square or something in there. So if we take a look at our graph coming back over here, oops, let me put it on screenshot there so I can sketch. So remember, this was a max. It was increasing in concave down to here. So, we don't know exactly how steep it's going to be, but we'll just kind of gander a guess at this point. And then so it's going to continue being concave down until it gets to there. Then it's going to switch. And remember, that's a min. So then we're going to have concave up. And then we're going to come down, hit that, concave up, and then go through our intercept right here that we found and continue increasing to infinity. So our shape should be something like that. And then we can check that over here, let the computer do the work, and see how close we get. And yeah, so you can see that we've got this part, we've got that, and then coming down here, we have that. Now, this right here, now remember, this is not actually a cusp. Let me go ahead and get that off of it because the derivative did exist. It's a fairly pointy extrema, but it's not a cusp because we actually had a derivative and the derivative was equal to 0 at that point. So even though it comes up and down, don't think that that's a cusp. We already proved it with our derivative formula that that was not a cusp on that. All right, but it is a fairly steep change there, pretty quick change going up and then down here with our concavity. All right, so that finishes that example out, and we will go on to example 7.